Hello everyone. Today's topic is on discrete mathematical structures whose subject code is 18CS36 under VTU. I'll be teaching a topic in module 4, Principles of Counting. And the topic name is Recurrence Relation. Myself, Dr. Madhura, working as an assistant professor in the Department of Mathematics, Sai Vidya Institute of Technology, Bengaluru. So in my last video, you would have seen about first order recurrence relation. Today, I'll be teaching about second order recurrence relation. And in our topic, we'll be talking about second order homogeneous recurrence relations. Let us first learn the definition, followed with the related formulas to do problems based on this. The standard form of the second order recurrence relation is given by Cn into An plus Cn minus 1 into An minus 1 plus Cn minus 2 into An minus 2 equal to 0. This is an expression for all n greater than or equal to 2. We can recognize it as a second order homogeneous recurrence relation since there are three terms involved, an minus 1 and an minus 2 in the expression. And since the RHS of the expression is 0, it is homogeneous recurrence relation, where Cn minus 1, Cn minus 2 are all real constants. We frame the auxiliary equation of equation 1, that is the standard form of the homogeneous recurrence relation, which is given by Cn into k square plus Cn minus 1 into k plus Cn minus 2 equal to 0. Let us see how we are actually framing this auxiliary equation. We are replacing an, the highest suffix, with k square. We are replacing an minus 1 by k, and finally an minus 2 by k power 0, which is 1. And if you observe, this is expression similar to the differential equations in mathematics, the ordinary differential equations. So framing the auxiliary equation, we find the roots of the homogeneous second order recurrence relation. And based on the nature of the roots, we will be writing down the general solution. Suppose, after solving the second order recurrence relation, we obtain k1 and k2 are the roots of the auxiliary equation. Then the following cases arises. Firstly, suppose the roots obtained k1 and k2 are real and distinct roots. Distinct means different. So suppose the roots that we obtain are real and distinct. Then the general solution of given equation will be of the form an equal to capital A into k1 power n plus b into k2 power n. K1 and K2, remember, they are the roots of the auxiliary equation, and A and B are the arbitrary constants, which we can obtain by using the given initial conditions. So this is the case 1 for us, where the roots of the auxiliary equation are real and distinct. Case 2, if K1 and K2 are equal roots, say suppose they are equal roots equated to K, then the general solution of such an equation is given by an equal to a plus b into n, the whole thing multiplied by k power n. So we will be getting a common root here. It is a second order recurrence relation, so obviously two roots will be obtained. Suppose both the roots k1 and k2 are equal, they are equated to say k, then General solution is of the form a plus b into n multiplied by k power n, where again capital A and B are arbitrary constants. And finally, one more case we have the roots of the auxiliary equation, that is k1 and k2, whatever we obtained, are imaginary roots. That is, suppose k1 equal to p plus iq and k2 equal to p minus iq. Then the general solution of equation 1 is of the form an equal to r power n into a cos n theta plus b sin n theta. So whenever we obtain the roots as imaginary roots, they always occur in pair, which is of the form p plus or minus iq. And we split the roots as p plus iq and p minus iq. And for such imaginary roots, the general solution is written in the form an equal to r power n into a cos n theta plus b sin n theta, where a and b are the arbitrary constants. We have r and theta also, and there is a separate formula for r and theta. R is given by square root of p square plus q square, where p is the real part and q is the imaginary part. So square root of real square plus imaginary term square. And theta is given by tan inverse of q by p. Tan inverse of q by p. So these are the different cases that can arise when we solve the second order recurrence relation by framing the auxiliary equation. Since we are talking about second order, we have two roots obtaining, and those two roots can be of these different possibilities. They can be real or distinct, they can be equal, or they can be imaginary roots. So based on the particular types, we'll be writing down the general solution. So this is a topic almost familiar to the ordinary differential equations, where we solve the second order differential equations, which is homogeneous. Let us see problems on second order homogeneous recurrence relations. Solve the following recurrence relation. First question, an plus an minus 1 minus 6 into an minus 2 equal to 0 for all n greater than or equal to 2, with the given conditions a naught equal to minus 1 and a1 equal to 8. So very firstly, we observe from the question that it is a second order recurrence relation since three terms are involved. An minus 1 and an minus 2 will help us to understand it is second order recurrence relation. So firstly, let us compare with the standard form of the second order recurrence relation, which is given by Cn into an plus Cn minus 1 into an minus 1 plus Cn minus 2 into an minus 2 equal to 0. So on comparison, we'll be able to write down Cn value is 1, Cn minus 1 value is also 1, and Cn minus 2 value is minus 6. Compare along with the sign and write it down. So Cn minus 2 is minus 6. Thus, the auxiliary equation will be given by Cn k square plus Cn minus 1 k plus Cn minus 2 equal to 0. Substitute the respective values what we obtain. So we get k square plus k minus 6 is equal to 0. Solving the second order equation using the calculator, we can directly obtain k value is minus 3 and k value is 2. So the two roots that we have obtained are k1 and k2, which are respectively minus 3 and 2. So roots of the auxiliary equation can be respectively written as k1 and k2, and these are real and distinct roots. They are different roots and they are real roots. So we write down the general solution of the given second order homogeneous recurrence relation as an equal to capital A into minus 3 whole power n plus capital B into 2 power n. The general formula from the theory says that it is k1 power n plus k2 power n. Of course, k1 and k2 can be reversed and written. That doesn't affect as the final solution. Now, we call this as equation 1 because we need to impose the given conditions on this general equation, general solution we obtained now, so that it will help us to obtain the arbitrary constants capital A and capital B. So let us apply the given conditions. A naught equal to minus 1, A1 equal to 8. In order to substitute the first initial condition A naught equal to minus 1, I have A suffix 0. So we take n equal to 0 in equation 1. Taking n equal to 0 in equation 1, we get A naught equal to capital A into minus 3 whole power 0 plus capital B into 2 power 0. Taking n equal to 0, we took n equal to 0 so that I can substitute for A naught. So substituting A naught as minus 1, anything raised to power 0 will be 1. So we get right hand side as A plus B. I was not able to individually obtain the constant A or B. So I need to solve it with another equation which I obtain by substituting the second initial condition. So I just call this as equation 2. Now we take n equal to 1 in equation 1 so that I can substitute A1 value as 8. So take n equal to 1 in equation 1. We get A1 equal to capital A into minus 3 whole power 1 plus B into 2 power 1. Simplifying this by substituting A1 value as 8, we obtain minus 3A plus 2B equal to 8. Now just observe equations 2 and 3. They can be solved simultaneously. You can use a calculator to solve them simultaneously. Two equations, two unknowns. Solving them, we obtain the value of capital A as minus 2 and B as 1. We now substitute capital A and capital B, the arbitrary constants, into equation 1, which is nothing but the general solution. So substituting, we have an equal to minus 2 into minus 3 whole power n plus 1 into 2 power n. A value is minus 2, capital B value is 1. So we get this expression which can be simply written as 2 power n minus 2 into minus 3 power n. So this gives us the complete solution of the given second order homogeneous recurrence relation. So this problem I took based on the nature of the roots. This was real and distinct roots. So based on that, we obtained the general solution, hence the complete solution. Let us see second problem. an minus 6 into an minus 1 plus 9 into an minus 2 equal to 0 for all n greater than or equal to 2. Given the initial conditions, a naught equal to 5 and a1 equal to 12. So this problem also goes in the same procedure what we did in the last one. Very firstly, we compare the given second order recurrence relation with the standard form Cn into An plus Cn minus 1 into An minus 1 plus Cn minus 2 into An minus 2 equal to 0. So on comparing, Cn value is 1, Cn minus 1 value is minus 6, Cn minus 2 value is 9. We now frame the auxiliary equation for this, which is of the form Cn into k square plus Cn minus 1 into k plus Cn minus 2 equal to 0. Substitute Cn minus 1, Cn minus 2. We obtain k square minus 6k plus 9 is equal to 0. If you observe, this can be directly written as well. You can just avoid the steps that you are comparing with the standard form and you have the values of Cn minus 1, Cn minus 2, and writing down the auxiliary equation also can be avoided. It is just an observation that An is replaced by k square, An minus 1 is replaced by k, and An minus 2 is replaced by k power 0. So directly also you can write down the auxiliary equation. Solving this auxiliary equation, we get the roots as 3 comma 3. Yes, it's an application of case 2, what we discussed in the theory. The roots are real and repeated or real and equal roots. So on comparing, we will write down k1 and k2 both are equal to 3. So the roots are real and repeated. Hence the general solution of the given second order homogeneous recurrence relation is an equal to a plus b into n whole thing into 3 power n. Recall from the theoretical concept, the general formula or the general solution for a real and repeated roots is of the form a plus b into n, the whole thing into k power n, where k is the common root, that is k1 equal to k2 equal to k. So here k value is 3, that's why 3 power n. So again we call this as equation 1, so that on imposing the given initial conditions, we should be able to find out the arbitrary constants, capital A and capital B. So let us now impose them one by one. From the data, A0 is 5 and A1 is 12. So substituting n equal to 0 in equation 1. So very firstly, we take n equal to 0 so that I can substitute A0 value as 5 in equation 1. So we have A0 equal to n equal to 0. So we get A0. N equal to 0, 0 into B gives us 0. So we have A into 3 power 0. 3 power 0 is 1. So we are getting A value as capital A equal to 5 because A0 is the initial condition known from the data, which is 5. Now we substitute n equal to 1 in equation 1. N equal to 1 so that I can impose the second condition A1 equal to 12. So we have A1 equal to, looking into equation 1, we are substituting. So A plus B into 1 multiplied by 3 power 1. A1 value is 12. So I have A plus B into 3. Where A value is 5, multiplying 5 into 3 it is 15 plus 3B. 3 is multiplied for both the terms. No, that's the reason. So on simplifying this, B value is equal to minus 1. Now once we have known with the arbitrary constants A and B, we can substitute into equation 1. So substituting A and B in equation 1, we obtain An equal to capital A value is 5, B value is minus 1. So it becomes minus 1 into n. So minus n into 3 power n. So this is the complete solution of the given second order homogeneous recurrence relation. So this problem was based on real and repeated roots. We'll consider another problem, which is dn equal to b into dn minus 1 minus b square into dn minus 2 for all n greater than or equal to 3 given d1 value is a constant b, which is a positive value, and d2 value is 0. So instead of giving the expression in terms of an minus 1, an minus 2, the question is framed in terms of dn minus 1, dn minus 2. That's all. So let us do the problem considering the given expression, taking all terms to left hand side, so that we will be able to compare to the standard form Cn into Dn plus Cn minus 1 into Dn minus 1 plus Cn minus 2 into Dn minus 2 equal to 0. And by comparing, Cn value is 1, Cn minus 1 is minus b, Cn minus 2 is b square. Thus, the auxiliary equation is given by, this is the formula for us, substituting Cn minus 1, Cn minus 2, we obtain k square minus b into k plus b square equal to 0. The expression b and b square are existing, so we cannot use a calculator and solve this. Let us do it manually by applying the formula minus b plus or minus square root of b square minus 4ac divided by 2a. So in place of a, I have 1. In place of b, it is minus b. In place of c, it is b square. So minus b, minus of minus becomes plus b here. Plus or minus square root of b square minus 4 into a into c. C value is b square. The whole divided by 2 into 1. A value is 1 in the denominator. So 2a gives us 2. Simplifying this, we obtain the roots as b plus or minus I into root 3b divided by 2. We observe we have obtained imaginary roots. Thus, k1 equal to b divided by 2 plus I into root 3 into b divided by 2, and k2 value is b by 2 minus I into root 3b divided by 2. So these are imaginary roots which are of the form p plus or minus iq. So on comparison, we can write down p value as b by 2 and q value is root 3b by 2. So we are just comparing with the standard form and able to write down p and q values. Therefore, the general solution of equation 1 based on the nature of the roots, that is the imaginary roots, we can write it down as dn equal to r power n into capital A cos n theta plus b into sin n theta. We need to find out r and theta and substitute into equation 1. Here a and b are the arbitrary constants which has to be obtained based on the given conditions, initial conditions. So we have r equal to square root of p square plus q square. Substituting p and q, we obtain this expression. Simplifying it is equal to b. Similarly, theta equal to tan inverse q by p, which can be written as tan inverse q value is root 3b by 2, p is b by 2. So we have tan inverse root 3, which is pi by 6, nothing but 60 degree. So once we have obtained r and theta, we substitute into the general solution, whatever we wrote it and call it as equation 1. We obtain dn equal to r power n, r value is b, so b power n into a cos the n theta, n into pi by 3 plus b sin n theta, so n into pi by 3. We have just substituted r and theta value. So we will be in need of this expression to impose the initial conditions which will help us to find out the arbitrary constants a and b. So we'll call this as equation 2. So this is our general solution. Now we'll obtain the complete solution by finding capital A and B. Let us rewrite the initial conditions given for us. D1 value is given, which is B. D2 value is given, which is 0 from the data. So we substitute n equal to 1 and n equal to 2 in equation 2 so that we can impose these values, initial values onto equation 2. We have d1 equal to b power 1 into n equal to 1 we are taking now. That's why b power 1 into a cos pi by 3 plus b sin pi by 3. D1 value is given, which is b. I have just substituted that in the LHS. Right hand side, we have simplified substituting the values of cos 60 degree and sin 60 degree, which is respectively 1 by 2 and root 3 by 2. So on simplifying this, we can rewrite it down as half a plus root 3 by 2b equal to 1. We could not find out a or b value directly, so we'll be solving this along with another equation, which we obtain by substituting n equal to 2 in equation 2. That is d2 equal to b square into a cos 2 pi by 3 plus b sin 2 pi by 3. Because we have taken n equal to 2. Now d2 value is given from the data as 0 equal to b square. Cos 2 pi by 3 can be written as minus cos pi by 3. Similarly, sin 2 pi by 3 can be written as sin pi by 3 using allied angles. Substituting cos pi by 3 and sin pi by 3, we have minus half a plus root 3 by 2b equal to 0. Now we have two simultaneous equations to solve. That is equations 3 and 4. By solving these equations simultaneously, we will be able to find out capital A and capital B values. So we get capital A equal to 1 and capital B equal to 1 divided by root 3. We now substitute capital A and capital B into equation 2, which we had called it as a general solution. So substituting in it, this was our expression which we had. B power n into A value is 1. So 1 into cos n pi by 3 plus B. B value is 1 by root 3 into sine of n pi by 3. So this is the complete solution for the given second order homogeneous recurrence relation, wherein the obtained roots were imaginary roots. I would like to consider one last problem. So question is fn plus 2 is equal to fn plus 1 plus fn for n greater than or equal to 0. Given the initial conditions f0 is 0 and f1 is 1. So let us rewrite the given equation firstly in order to get it to the standard form. We recall the standard form, which is of the form Cn into An plus Cn minus 1 into An minus 1 plus Cn minus 2 into An minus 2 equal to 0. Instead of An minus 1, An minus 2, I can have the expressions in terms of f. But we observe that I have expressions with respect to n plus 2, n plus 1 and n. So we are trying to rewrite the given equation as fn equal to fn plus 1 plus fn equal to fn minus 1 plus fn minus 2 for n greater than or equal to 2. So we are just replacing the highest suffix n plus 2 by n. The next highest suffix is n plus 1, which can be replaced by n minus 1. And finally, the suffix n can be replaced by n minus 2. That is how we will be able to rewrite the given equation. And this becomes a valid expression for all n greater than or equal to 2. So solving or comparing this equation with the standard form, first we take all the terms to the left hand part. So we have fn minus 1 minus fn minus 2 is equal to 0. Now we frame the auxiliary equation for this. Fn is replaced by k square, fn minus 1 is replaced by k power 1, fn minus 2 is replaced by k power 0. So we get the second order equation as k square minus k minus 1 is equal to 0. Solving this, we obtain the roots as 1 plus or minus root 5 divided by 2. I've purposefully done it manually using the formula minus b plus or minus square root of b square minus 4ac divided by 2a. Since the values which you observe here are the decimal values, instead of writing down the decimal, I've just thought of writing down in the fractional form 1 plus root 5 divided by 2 and 1 minus root 5 divided by 2. So roots of the auxiliary equation are written as k1 and k2. Observe, these are not imaginary roots, they are real and distinct roots. There's no I involved here. So they are real and distinct roots. So therefore, the general solution of equation 1 is given by Fn equal to, given equation was in terms of F. So we are writing down the general solution for Fn, which can be written as A into k1 power n plus b into k2 power n. k1, k2 are real and distinct values. So I've substituted those real and distinct values and written this equation 2. We need to impose the given conditions f0 is 0 and f1 is 1 on this equation to obtain the arbitrary constants capital A and capital B. So let us impose those conditions one by one. Substituting n equal to 0 in equation 2, we can obtain f0 equal to a plus b. N equal to 0, so left hand side will give us f suffix 0 and right hand side we have 1 plus root 5 divided by 2 whole power 0 and 1 minus root 5 whole divided by 2 whole power 0. Anything raised to power 0 gives us 1. So we have f0 as a plus b. So f0 value is 0 given. So this can be written as a plus b equal to 0. Now, substituting n equal to 1 in equation 2, we can obtain f1 expression. So n equal to 1, so f1 equal to a into 1 plus root 5 divided by 2 power 1 plus b into 1 minus root 5 divided by 2 power 1 raised to power 1. So I have retained the expression as it is, substituting f1 value as 1 from the data, which is equation 4 for us. Now once again, we need to solve for capital A and B from equations 3 and 4. And I have done it manually so that we can have the fractional values for capital A and capital B. So let's see how is it. Let us multiply equation 3 by 1 plus root 5 divided by 2. I'm trying to take common expressions so that when I subtract them, I can cancel off with capital A and obtain the B value. That's how we solve any simultaneous equations manually, right? So multiplying equation 3 by 1 plus root 5 divided by 2, we get 1 plus root 5 by 2 into A plus 1 plus root 5 divided by 2 into B equal to 0. I have manipulated equation 3. Now observe equation 4 and 5. The expression for A is common, so I can just subtract equation 4 and 5 so that A cancels and we can obtain an answer for B. So equations 4 and 5, we subtract 4 minus 5 to get 1 minus root 5 divided by 2 minus of 1 plus root 5 divided by 2 into B equal to 1. So simplifying this, b value is equal to minus 1 by root 5. Now once we have known one of the value from equation 3, we have a plus b equal to 0 or a value is minus b. So substituting b value in this, a can be obtained as 1 divided by root 5. Usually this is the way we solve a simultaneous equation in the manual manner without using a calculator. And we did this without using calculator only because we can have the fractional values of capital A and B as it is. Now we substitute capital A and B into equation 2, which will help us to obtain the complete solution. So Fn equal to 1 by root 5 into 1 plus root 5 divided by 2 whole power n minus 1 by root 5, b value is minus 1 by root 5 into 1 minus root 5 divided by 2 whole power n. Taking 1 by root 5 common, we can write down the complete solution for the given second order homogeneous recurrence relation in the form Fn equal to 1 by root 5 into 1 plus root 5 divided by 2 whole power n minus of 1 minus root 5 divided by 2 whole power n. Hope you have followed these problems based on second order recurrence relation. I've given some practice questions so that you can get more clarity in these topics. Solve the following recurrence relations. Some questions are based on A, some questions are based on C expression. So these problems working will help you to have a better clarity on the topic. Thank you for watching.